Forgot again. Here we go. All right. All right, so geometric sequences and series. Definition, what is a geometric sequence? Well, ladies and gentlemen, any sequence that looks like this, where our first term is a sub 1 and our second term is our first term times some number called r, and our third term is the previous term times that number r, and the fourth term is the third term times that same number r, etc., etc., is called a geometric sequence. Okay. Now, an arithmetic sequence has a common difference, but a geometric sequence has what's called a common ratio. Common ratio. And as it turns out, ladies and gentlemen, your common ratio is going to be like your second term divided by your first term, or it'll be your third term divided by your second term, or it'll be your fourth term divided by your third term, or it'll be your fifth term divided by your fourth term, etc., etc., etc. It's called the common ratio. Specifically, a sub 1 is our first term. Our second term is obtained by taking your first term and multiplying it by the common ratio. Your third term is obtained by taking your second term and multiplying it by the common ratio. But ladies and gentlemen, our second term was the first term times the common ratio, so I can substitute this value in here for my second term, and that's to say that it's really our first term times the common ratio again, which is to say the first term times the common ratio squared. Everybody see that there? Our fourth term is really the third term times the common ratio, but we have a name for the third term. It's the first term times the common ratio squared, which can get substituted in for your third term, in which case we have the first term times the common ratio squared times the common ratio, which is to say the first term times the common ratio cubed. The fifth term is really the fourth term times the common ratio, but the fourth term we discovered is the first term times the common ratio cubed. So therefore, your fifth term is the first term times the common ratio cubed times the common ratio, which is to say the first term times the common ratio to the fourth power. Ladies and gentlemen, do you see any pattern here? In general, what can I call my nth term of my geometric sequence? Anybody see a pattern? Well, let me draw your attention to this pattern here. Notice we start off with a sub 1, our first term, which is technically your first term times your common ratio to the 0th power. A sub 2 has the first term times the common ratio to the first power. The third term is the first term times the common ratio to the second power. The fourth term is the first term times the common ratio to the third power. The fifth term is the first term times the common ratio to the fourth power. In general, what's the relationship between the index of the term and the power on R? What's the relationship?
The power on R is n minus 1.
It lags 1 behind. So therefore, the nth term of a geometric sequence is the product of the first term of the geometric sequence times the common ratio raised to the n minus 1 power. This is a very important formula. This, ladies and gentlemen, is called the nth rule for a geometric sequence. Nth rule for a geometric sequence. This rule will enable you to crank out any term of a geometric sequence so long as you know the first term and its common ratio. So this is a wise one to have in your memory banks, or at least to have handy. You'll need to know that rule. So in general, ladies and gentlemen, we've seen above here that your common ratio is always a term divided by the previous term. So we could say in general, your common ratio is always the n plus 1th term divided by the nth term. Does that make sense? It's always the n plus 1 term divided by the previous term, which is the nth term. The nth term is one term previous to the n plus 1th term of the sequence. A recursive definition for a geometric sequence is to say that your nth term of your geometric sequence is always the previous term, denoted as the n minus 1th term, times your common ratio. And this is valid for n to be greater than or equal to 2. This is called a recursive definition for a geometric sequence, or recursive rule, if you will. So notice a recursive rule always, in order to find a term using a recursive rule, you always have to revert back to a previous term or previous terms. The nth rule just enables you to basically plug in the value for n to generate any term of a sequence directly. So we've seen that recursion, is a little bit more cumbersome to arrive at, let's say, the 10th term of a sequence, as opposed to just using the nth rule. Okay. Any question about anything on that page so far there? Any questions? All right, so we're talking about geometric sequences here so far. Everybody have this page accounted for? Take that as a yes. All right. Let's try to answer this question or these questions. Is the following sequence geometric? Well, to be a geometric sequence, ladies and gentlemen, a sequence has got to have a common ratio. If it doesn't, it's not a geometric sequence. It's some sort of other sequence. If we look at this sequence here, which appears to be an infinite sequence, is it geometric? Well, if it's geometric, then we must have a common ratio. So is our common ratio, does it exist? And if it does exist, is it to say that it's 6 divided by 18? Which is also should be equal to 2 divided by 6, which should also be equal to 2/3 divided by 2. Is that true? What's 6/18? What does that reduce down to?
1/3.
1/3. Is 2 divided by 6 also 1/3? Looks like it is. Is 2/3 divided by 2 1/3? 2/3 divided by 2 over 1 is 2/3 times 1/2, which, believe it or not, is also 1/3. Ladies and gentlemen, it looks therefore like our common ratio is what? 1/3. And so is this sequence geometric? The answer is, what do you like?
Yes.
The answer is yes, it is a geometric sequence because it possesses a common ratio, which is 1/3. Everybody understand that? It's a geometric sequence. In other words, to move from any term to the next term, you have to multiply the term by 1/3. So if you take 18 times 1/3, you get 6. If you take 6 times 1/3, you get 2. 2 times 1/3, you get 2/3. Okay. So it is a geometric sequence. All right, we'll call that problem A. Problem B, is this sequence geometric? 3, 12, 48, 240. Is this infinite sequence geometric? Do we have a common ratio? Is 12 divided by 3, is that equal to 48 divided by 12? Is that equal to 240 divided by 48? Yes or no? Do we have a common ratio? Is 12 divided by 3 is 4. 48 divided by 12 appears to be 4. 240 divided by 48, use your calculator. What is 240 divided by 48? Is it 4? Is that 4? What's 240 divided by 48?
It's 5.
Uh-oh. Since not all these ratios are equivalent to the same number, ladies and gentlemen, there is no common ratio. So this is not a geometric sequence. Does not possess a common ratio. Any questions about what a sequence is or has to be if it's to be geometric? It has to have a common ratio. If it doesn't, it's not a geometric sequence. This is not geometric because this ratio is not equal to all the other predecessors. All right. All right, let's try this problem here. Let's try to write the first 5 terms of the geometric sequence. So I'm telling you it's geometric. Where a sub 1 is equal to 5 and r is equal to -2. So ladies and gentlemen, we want to write the first 5 terms of this geometric sequence. What's my first term? What's my first term?
5.
5. How do we find the second term?
Multiply first one by -2.
Multiply the first term by the common ratio. So we got to multiply 5. We got to multiply 5 times -2. So the second term would be -10. How do you find the third term? How do you find the third term?
You do a sub 1 times r squared.
You can, yeah, you can do this one of 2 ways. You can take your first term times the common ratio squared, or that's to say you can take your second term times the common ratio. Either way, it's up to you. So if you go the first term times your common ratio of -2 squared, that should give you the same thing as if you took the second term, which is -10 times your common ratio. You agree? In either case, we should get what? 20?
Yep.
20 would be the third term of that geometric sequence. What's the fourth term? The fourth term is just the third term times the common ratio, or it would be the first term times the common ratio to the third power. Either way. So if you want to go the third term, which is 20 times the common ratio of -2, that would be equivalent as if you take the first term of 5 times the common ratio of -2 cubed. Either case, you should get what? -40. That would be your fourth term. Finally, the fifth term of the geometric sequence, I'm just going to say is my fourth terms times the common ratio, which would be -40 times -2, which would be 80. And that could also have been found if you took your first term times the common ratio to the fourth power. All right, so here's your first 5 terms of that geometric sequence. 5, -10, 20, -40, and 80. Ladies and gentlemen, we call this an alternating geometric sequence. Why alternating?
Because the values like flip from negative to positive.
Yes, because the sign alternates, positive, negative, positive, negative, positive, negative, positive, negative. It's an alternating geometric sequence. That's what we have there. All right, alternating geometric sequence. Okay, any questions how we wrote the first 5 terms of that geometric sequence, given the first term and its common ratio? All right, these are classic textbook problems that I'm doing and classic Alex problems that you'll be encountering. So it's important to understand these. If you don't, let me know if you don't understand something. Okay, let's look at this one here. Let's try to write the nth rule for the geometric sequence. And ladies and gentlemen, they give us the first few terms of this geometric sequence: 2, 3, 9 halves, 27 fourths, etc., etc. Given these first 4 terms of this geometric sequence, can we derive or come up with the nth rule for this geometric sequence? Well, do you remember the nth rule that I derived a couple pages back? How did that go? To write the nth rule of any geometric sequence, to find any nth term of a geometric sequence, what was the rule? Do you remember? What was that formula?
It was A1 times R2 to the power of n minus 1.
There you go. This, ladies and gentlemen, is going to help us write the nth rule for this geometric sequence. So again, this is a wise thing to, either have handy, or if you're going to go onwards in mathematics, I would just commit that to memory. Okay. All right. Now to write this nth rule, we're going to need to know what? We're going to need to know the first term of the sequence, and we need to know the common ratio. What is my first term for this geometric sequence? The first term.
2.
Yeah, it's 2. That is your first term. That's a sub 1. So your first term is 2. Now, what's the common ratio? Well, it's got to be equal to what? In general, your n plus 1th term divided by the previous nth term. So it better be equal to 3 divided by 2, or better be equal to 9/2 divided by 3, or it better be equal to 27/4 divided by 9/2. And ladies and gentlemen, even if you take these nasty fractions and try to divide them, you'll see that you better get 3/2. For instance, I'll convince you. Let's try this one. 27/4 divided by 9/2 is 27/4 times 2/9, which through cross canceling, this goes into sum 1, goes in 27 3 times. 2 divides the sum 1, goes into 4 twice. You do get 3/2. Yes, it looks like our common ratio is 3/2. Therefore, the nth rule for this geometric sequence is very easy to write. A sub n is equal to your first term, which is 2, times your common ratio, which is 3/2, raised to the n minus 1 power. Done with problem. We have written the nth rule for that geometric sequence. Does that make sense? That would be the nth rule that would generate any term of this infinite geometric sequence. Any term. You think it would? For instance, what term is this? 27/4 is what term?
The 4th term.
It's the 4th term. Let's see if we get that, if we let n be 4 in this nth rule. Let's let n be 4. So my 4th term should be 2 times 3/2 raised to the 4 minus 1 power, meaning my 4th term should be 2 times 3/2 raised to the 3rd power, meaning that my 4th term better be 2. What's 3/2 cubed? 3 cubed is 27. 2 cubed is 8. What's 2 times 27/8? Do you agree? The 2 and the 8 cross cancel, cross reduce, and we get 27/4. Ladies and gentlemen, we do get the 4th term. Looks like this is indeed the nth rule for that geometric sequence. Okay. Any questions how we derive the nth rule for that geometric sequence? All right, that's a very typical problem. Here's another one now. Suppose we want to find the 5th term of the geometric sequence, denoted as in braces, a sub n. Remember, that's a general way of representing any sequence we've seen way back in section 8.1. Given that the first term of the geometric sequence is 15 and the second term of the geometric sequence is -9. Knowing the first term and the second term, ladies and gentlemen, we should be able to write the 5th term for this geometric sequence. How to do that? Well, we could use our what? Nth rule formula, which is to say, to generate any nth term of this geometric sequence, it's the first term times the common ratio raised to the n minus 1 power. I need to know the first term. Do I know the first term? Yes, it's 15. Do I know the common ratio? No, but I can find it. How? How can I find my common ratio? How do we find the common ratio?
Divide the second term by the first term.
Yep, divide the second by the first term, which is to say -9 divided by 15, then it reduces down to what? -3/5. So my common ratio is -3/5. Now we're in business, because our specific nth rule for this geometric sequence is going to be a sub n is equal to the first term, which is 15, times the common ratio, which is -3/5, raised to the n minus 1 power. We can now use this rule, ladies and gentlemen, to generate any term of this geometric sequence. They want us to find the fifth term. Easy. All we do is let n be 5 in this nth rule, and we'll crank out the fifth term. So the fifth term of this geometric sequence is going to be 15 times negative 3/5 raised to the 4 minus 1 power, raised to the 5 minus 1 power, excuse me. Therefore, the fifth term is going to be 15 times negative 3/5 raised to the 5 minus 1, or raised to the 4th power. What is negative 3/5 to the 4th power? Well, when you raise a negative to an even power, it's going to be positive, guaranteed. 3 to the 4th power is 3 times 3 times 3 times 3, which is what, 81? 5 to the 4th power is 5 times 5, which is 25, times 5 is 125, times 5 is 625. And ladies and gentlemen, I think we can cross reduce here. Doesn't 15 divide into 625? How many times? Can anybody dial that up? How many times does 15 go into 625 here?
It's 41.666.
All right. I would like my fifth term to be in just as a fraction, reduced fraction. Look at 5 will go into 15 3 times. 5 goes into 625 125 times. 3 times 81 is 243. So my fifth term is going to be 243 over 125. Ladies, I'm going to leave it like that. That's my fifth term. Just leave it as a reduced fraction. So my fifth term of this geometric sequence is 243 over 125. We're done with that problem. Okay. Oh, by the way, Caleb, is it?
Yeah.
You could have taken that decimal and hit your math button and selected the frac function. It would turn it back into a fraction. Wouldn't it? Try that out. I think you turn this into a decimal, but turn it back into a fraction. Does it give you that back?
Oh, 1 sec.
It should give you back the fractional form of that. Use the frac function in math.
Yep, I got it back.
All right. Questions, ladies and gentlemen. How, if I give you some terms of a geometric sequence, do you think you're going to be able to generate any given requested term? That's a classic typical problem involving geometric sequences right there. Okay. All right. Any questions about anything on this page here? Okay. All right, let's try this one. Given the second term is 18 and the fifth term of a geometric sequence is 144, they want us to find the first term, the common ratio, and they want us to find the nth term. That's what they want us to find. They're going to give us the second and the fifth term of this geometric sequence. They want us to find the first term, common ratio, and the nth term. So they give you the second term is 18. And the fifth term is 144. They want you to find the first term right here. They want you to find the common ratio. And they want you to find an nth rule in general. Okay. So how are we going to do that? Well, you know, we can make use of the nth rule. So using our nth rule, our general nth rule for a geometric sequence, we will use this. We know what? We know our second term is equal to 18. So this would imply that if I use my nth rule and let n be 2, my second term is going to be equal to my first term, which we don't know, times our common ratio, which we don't know, raised to the 2 minus 1 power. But we know our second term. Our second term is 18. So 18, therefore, must be equal to our first term times the common ratio raised to the first power. Put a box around that equation. Using the nth rule, the skeletal form of the nth rule again, we also know what else? We know that the fifth term of this geometric sequence is 144. That would therefore imply that our nth rule would take on the form when we let n be equal to 5. It would be equal to our first term times the common ratio raised to the 5 minus 1 power. But we know our fifth term is 144, so we replace it with 144. That's equal to our first term times our common ratio raised to the 4th power. Put a box around this. Everybody understand how I got those two equations there? All right. Well, ladies and gentlemen, if I use this equation here, suppose that I solve for, let's say, a sub 1. How would I solve this? How would I solve this for a sub 1? How do I solve for a sub 1?
Divide both sides by r.
Yeah, because we have a system of two equations and two unknowns. We have a sub 1 as being unknown and our common ratio is unknown. So we're going to solve this system. We'll solve it by substitution. So I'm going to solve this first equation by a sub 1 by dividing both sides by r. So a sub 1 is 18 over r. I can now take 18 over r and substitute it in for the first term in the second equation, substitution method. Therefore, the second equation upon making that substitution is 144 equal to 18 over r times r to the 4th. 144 is equal to 18 r to the 4th divided by r. But what's r to the 4th divided by r? That implies that 144 is really equal to 18r cubed. And now, ladies and gentlemen, we can solve this equation for what? For r. Divide both sides by 18. That isolates r cubed. Now, what's the inverse of cubing something?
The cubed root.
So now we take the cubed root of both sides of this equation. Get on your calculator, ladies and gentlemen, hit your math button. Go down and grab the cubed root function. What is the cubed root of 144 over 18? Math button. Go down, grab the cubed root function. What's the cubed root of 144 over 18?
I got 2.
All right, so the common ratio for this geometric sequence is 2. Now, what's the first term of the geometric sequence? Well, we go back up to this equation here. Put 2 in for r, and we get our first term as being 18 divided by 2, or
9.
It's 9. So our first term is 18 divided by 2, or 9. So what have we discovered? We discovered the first term of this geometric sequence is 9. We know the common ratio is 2. Ladies and gentlemen, we can now find the nth rule. The nth rule for this geometric sequence is going to be equal to our first term times the common ratio raised to the n minus 1 power. Hence, the nth term of this geometric sequence is the first term, which is 9, times the common ratio, which is 2, raised to the n minus 1 power. There's your answer. That would be the nth rule for this geometric sequence. We've answered the question. We found the first term, found r, found the nth rule. We understand how we just found all that information about that geometric sequence there. All right. That's a classic problem there. So knowing our second and fifth term was enough to generate all this information about that geometric sequence. Okay, let's see what the clock is saying. 3:04. Okay. All right, ladies and gentlemen, classwork number 1. We'll call this classwork number 1. Today is the 15th day of December. There's only 10 days left. Well, Actually, only 9 days left for Christmas shopping. Classwork 1, December 15th. Number 1. I want you to write the formula for the nth rule of this sequence here. Number 2, given the first term of a geometric sequence is 12, given the second term is -8, I want you to find the 6th term. In other words, find a sub 6. Okay, all right, we'll call that classwork classwork number 1, ladies and gentlemen. All right, problem number one, they give you a geometric sequence. You want to find the nth rule, and this is your nth rule in general for any geometric sequence. We need to know the first term. We need to know the common ratio. The first term would be -2. Common ratio would have to be what? -1 divided by 2, or -1/2 divided by -1, or any term divided by the previous term, which would be 1/2. Then we just write our nth rule. Okay, the nth rule of that geometric sequence would be this right here. Anybody get that correct?
Yes.
All right. Now, the second one, they give you the first term and the second term. They want you, therefore, to find the sixth term of this geometric sequence. Well, since they give you the first and second term, we can immediately crank out the common ratio just by dividing the second term by the first term. So the common ratio turns out to be -8/12, which reduces down to -2/3. We know the first term is 12. Therefore, we can write the nth rule for this geometric sequence. And then we can use that nth rule to generate the sixth term of the sequence. So the sixth term, as it works out, ultimately comes all the way down to -128/81. Anybody get that correct?
Yes, I did.
All right, any questions, ladies and gentlemen, on any of those questions? Classwork number one. All right. Okay, well, let's move on. Let's start getting into geometric series now. A series, remember, is the sum. A series is a sum of terms of a sequence. Okay, so a series is a sum. A sequence is just a function. Okay, all right, we say the nth partial sum, denoted as S sub n, of the first n terms of a geometric sequence is a finite geometric series. So this is the definition of what a finite geometric series is. Let's consider this. Let's consider the nth partial sum of a geometric series, or a geometric sequence, the nth partial sum of a geometric sequence, where the first term is a sub 1, added to the second term, which is your first term times your common ratio, added to the third term, which is your first term times your common ratio squared, added to the fourth term, which is your first term times the common ratio cubed, plus on and on this goes, plus your first term times your common ratio to the n minus 1 power. Okay, so let's consider this nth partial sum, where we add together the first n terms of a geometric sequence. Check this out, ladies and gentlemen. Suppose we subtract r times the nth partial sum from the nth partial sum. Something interesting occurs. So let's take our nth partial sum again. And we're going to subtract off r times our nth partial sum. Which, when you take r times your nth partial sum above, you're going to have a sub 1 times r plus a sub 1 times r squared plus a sub 1 times r cubed, because every one of these terms gets multiplied by r. Plus all the way this goes to a sub 1 times what? What's r to the n minus 1 power times another r? When you multiply like bases, you add exponents. So this can be r to the what? N minus 1 plus 1, which is equal to r to the what? Nth? See that there? Well, let's subtract this off, ladies and gentlemen. When we subtract the left side of this equation, we have our nth partial sum minus r times your nth partial sum. And that's equal to term-wise subtraction here. A sub 1 minus this gives you a sub 1 minus a sub 1 r plus a sub 1 r minus a sub 1 r squared is going to be a sub 1 r right, minus what? A sub 1 r squared. Plus, on and on as goes. Take this, subtract this. You would have a sub 1 r n minus 1 power minus a sub 1 times r to the nth. Now look what happens. You agree that this minus a sub 1 r combines with this positive a sub 1 r. What happens to the a sub 1 r's? They cancel out. You agree, ladies and gentlemen? Well, it's hard for you to see this, but this term would cancel out the next one here. This would also be gone. And this would cancel out the previous term to that. You know what we're going to be left with here when we do all the cancellation of successive terms? We're going to have the nth partial sum minus r times the nth partial sum is equal to your first term that survives minus your first term times r to the nth power at the very end that survives. Now to solve for the nth partial sum, we first of all factor out our nth partial sum on the left side of our equation, leaving behind 1 minus r. That's equal to a sub 1 minus a sub 1 times r to the nth. Dividing both sides by 1 minus r, we therefore generate a very important formula. This formula generates the sum of the first n terms of a geometric sequence. It's going to be this formula right here. Divide both sides by 1 minus r. In the numerator, I can factor out the first term, a sub 1. So this is your nth partial sum formula for a geometric sequence. There you go, ladies and gentlemen. That's an important formula. That formula there will enable you to compute the sum of the first n terms of any geometric sequence. This formula will enable you to find the nth partial sum of any geometric sequence. Save you a whole lot of work. That formula there. The derivation of this is also in your textbook in section 8.3. They might show a couple more terms here to show you how these successfully drop out, cancel out. Okay. I just thought I'd show you that there. So again, that's a pretty important formula. Might want to have that one handy, as that can answer quite a few questions too, involving geometric series. Okay. Any questions? That's with what's on this page here. All right. Let's try to evaluate this series here. I goes from 1 to 6. We're going to try to evaluate this series. It's a series because this is called our summation notation, which means we're going to be adding terms of a sequence together. And notice we're going to be adding the first, how many terms are we going to be adding together? The first how many terms?
6.
First 6 terms. Terms 1, 2, 3, 4, 5, and 6. Okay. All right, let's generate, what the heck? Let's just generate, ladies and gentlemen, these terms here. So if you let I start off at 1, our first term is going to be 4 times 1/2 raised to the 1 minus 1 power. Second term is going to be 4 times 1/2 raised to the I increments to 2, 2 minus 1 power. Third term is going to be 4 times 1/2 raised to the 3 minus 1 power plus 4 times 1/2 raised to the 4 minus 1 power plus 4 times 1/2 raised to the 5 minus 1 power plus 4 times 1/2 raised to the 6 minus 1 power. Which is to say, is going to be 4 times 1/2 to the 0 power. What's 1/2 to the 0 power?
0.
No, what's anything raised to the 0th power equal to?
0.
No, not 0. Try that on your calculator. What's 1/2 raised to the 0 power?
Is it just 1/2?
No. What's anything raised to the 0 power equal to?
1.
1. 1. 1/2 to the 0 power is 1. This is going to be 1/2 to the 1st power. So it's going to be plus 4 times 1/2. This is going to be 1/2 to the 2nd power. 4 times 1/2 squared plus 4 times 1/2 cubed plus 4 times 1/2 to the 4th plus 4 times 1/2 to the 5th. Correct? All right. Well, in order to find the sum of the first 6 terms, we could use our partial sum formula, which we derived, and that's your first term times 1 minus r to the nth power divided by 1 minus r. We just derived that formula. To find the sum of the first 6 terms here, we need to know our first term. What is our first term in this sequence? The first term would be 4. That's your a sub 1. 1 minus, what's my common ratio? What do you think the common ratio is, ladies and gentlemen?
1/2.
1/2. Yeah, you can see it's 1/2. You can see way back over here, your common ratio is 1/2. So minus 1/2 raised to the what? Nth power, n is 6, so raised to the 6th power. Divided by 1 minus your common ratio. Get on your calculator, ladies and gentlemen, you can dial up the sum of the first 6 terms here. Instead of adding these together the hard way, why not just use this formula here? This will generate the sum of these first 6 terms here. So you're going to need a calculator, because unless you want to raise 1/2 to the 6th power, which you can do that, but I'm allowing you to just generate this whole sum on your calculator. I would like the sum either as a whole number, as an integer, or as a reduced fraction. So if you get a decimal, just hit your math button and select the frac function to convert it into a fraction. So let's see if we can crank that out.
I got 63/8.
Okay. So 63/8, yeah. And that would be the sum here of the first 6 terms. Or as a decimal, it would be 7.875. That would be the sum of all these terms here. Okay. So, and now this formula would be even more valuable if I wanted you to find the sum of like the first 100 terms, correct? Where, it'd be very, very awkward to do it the long way. This formula becomes even more attractive. All right. 63/8. Does that make sense how we found that? Okay. All right, let's try another one here. We'll try to find the sum of the geometric series. Is this a finite or infinite geometric series? What do you think? Finite or infinite?
Finite.
It would be finite because you don't see plus dot, 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 all right? So this is a finite geometric series. Finite geometric series. Okay. We don't know how many other terms there are in between here, do we? We don't have a clue. All we know is this is our what term?
First term.
That's your first term. We know this is our second term of our sequence. We know this is our third term, etc. Ladies and gentlemen, we don't know what term this is. We don't know if this is the 10th term or the 20th term or the 15th term. We don't have a clue. We'll call this in general the nth term. Anybody see that there? Nth term. Now, so what do we know? We know our first term of this geometric sequence is 1, of the associated geometric sequence is 1, and we know the nth term is this 32 over 243. So ladies and gentlemen, we don't even know how many terms we're adding together here, because we don't even know what term this is. We don't know if that's, again, we don't know if that's like the 7th term, the 10th term, the 15th term, the 100th term. We don't have a clue. So what we can do is we're going to have to find out what term this is here. In order to do that, ladies and gentlemen, we're going to use the associated geometric sequence, which is this right here. And we're going to have to find what term this last term is here. Well, we know our first term is 1. What's my common ratio? Can we determine that? Well, remember, the common ratio is always the ratio of a geometric sequence's term divided by the previous term. So this will be 2/3 divided by 1. Looks like your common ratio is 2/3. So now we know the common ratio is 2/3. We know the first term, we know the common ratio. Therefore, using the nth rule, and this is the nth rule here, I think we can derive for ourselves the nth rule here. Therefore, we know that our nth rule is going to be the first term, which is 1, times the common ratio, which is 2/3 raised to the n minus 1 power. But ladies and gentlemen, remember, we got to try to find what term this last term is here, so we can try to figure out how many terms we're adding together here. We don't even know what term this is. We know it's called the nth term in general. So therefore, using this nth rule I developed down here, I can let a sub n be equal to 32 over 243. And that's equal to 2/3 raised to the n minus 1 power. And now, ladies and gentlemen, what we're having to deal with here now is we're having to solve what's called an exponential equation. This is called an exponential equation. We got to solve for n. How do you solve for n, which is part of an exponent here? Has anybody ever solved an exponential equation like this? Got to solve for n. This is called an exponential equation. Has anybody ever solved one of these before? How do we solve for n? Well, one popular way to solve for n in this exponential equation is to reduce both sides of this equation down to the same base. Well, the right-hand side is base 2/3. Wouldn't it be great if I could somehow reduce this left side down to 2/3 raised to some power? But what power would that be? In other words, ladies and gentlemen, I'm trying to reduce 32 over 243 down to 2/3 raised to some power. What power do you have to raise 2 to get 32? You can get on your calculator and try that out. 2 to what power is 32?
The 5th power.
All right, so 2 to the 5th power is 32. What power do you have to raise 3 to get 243?
The 5th.
The 5th power. Well, it looks like we're in business. So we'll just raise 2/3 to the 5th power. And that's how we would generate the 32 over 243. Now, to solve this exponential equation for n, we tap into a theorem. And this theorem says this: if a to the mth power is equal to a to the nth power, then, ladies and gentlemen, what would have to be true about the exponents? What do you think? The exponents would have to be equivalent to each other. Does that seem reasonable? That seems pretty reasonable, intuitive, doesn't it? Unlike most theorems, this one's very intuitive. So therefore, since I have the equivalence between like bases, I should be able to equate the exponents. So therefore, 5 has to be equal to n minus 1, which implies then that n is equal to 6. So ladies and gentlemen, I have a question for you. What term is this term 32 over 243? It's our what term?
The 6th term.
It's our 6th term of the sequence. Everybody see that there? So therefore, this is really your 6th term. So we know we're adding together the first 6 terms of a geometric sequence. So now that we know we're adding together the first 6 terms of a geometric sequence, we can turn it over to our nth partial sum formula we derived. Therefore, we really need to find S sub 6, which is found by taking your first term of your geometric sequence times 1 minus the common ratio raised to the 6th power divided by 1 minus r. That will compute the sum of the first 6 terms of this geometric sequence. What is the first term of this geometric sequence? First term is what? 1, right? 1. What's my common ratio? We found the common ratio to be 2/3. And that's raised to the 6th power. All divided by 1 minus 2/3. Let's get on our calculators. I'll make sure you enclose your numerator and denominator side parentheses, or else you're going to get a logical error. Let's see if you can crank that out on the TI-84. I would like, a reduced fraction would be cool. Let me know if anybody gets that.
I got 665 over 243.
Real mess. 665 over 243. I would not have a meltdown if you did give it to me as a fraction, though. I mean, you can do that if you want. But it's a messy fraction. The messy decimal, isn't it?
Mm-hmm.
So this would be approximately equivalent to about 2.737 about. That's just an approximation. I rounded it off and truncated it. And that problem make any sense, ladies and gentlemen, how we found or evaluated this geometric series here? To do so, to recap, we had to what? We had to find what term that last term was. We had to determine that it was a 6th term. Because otherwise you don't know how many terms you're adding together. You could be adding, 10 terms together, or 100 terms, 1,000 terms, I don't know. So to find what term that was, I determined my first term, my common ratio, And then I use the nth rule. And the nth term, I let it become the 32 over 243. Then I solve this exponential equation for n here to determine that that was my sixth term of my sequence. Okay. Sixth term of the sequence. Any questions with how we did that problem there? Any questions? Okay. All right. Well. All right. So far, all of these geometric series, ladies and gentlemen, have been finite geometric series, in which case we, in order to compute them, we've used the nth partial sum formula here. But ladies and gentlemen, what happens if our series is not finite? What happens if it's infinite? How can we compute an infinite geometric series? Is that even possible? Well, that's what we're going to turn our attention to next. So consider the infinite geometric series. Suppose I have this infinite geometric series. 1/2 added to 1/4 added to 1/8 added to 1/16 added to 1 over 32 added to 1 over 64 plus 1 over 128 plus 1 over 256 plus ... plus, what's my common ratio, ladies and gentlemen? What's 1/4 divided by 1/2? Well, that's 1/4 times 2 over 1, which is 2/4, which is really what? 1/2. Common ratio is 1/2. So ladies and gentlemen, we have what's called an infinite geometric series because we have plus ... This thing goes on forever. Okay? Goes on forever. I have a question for you. Are the terms of the associated geometric sequence, the associated geometric sequence is 1/2, 1/4, 1/8, 1/16, 1/32, 1/64, 1/128, 1/256, 1 over 512, ... What do you notice about the terms of this geometric sequence, ladies and gentlemen? Are the terms getting larger or are they getting smaller?
Smaller.
Smaller. It looks like these fractions are getting smaller and smaller and smaller and smaller and smaller. So we keep adding, notice this infinite geometric series keeps adding fractions that are getting smaller and smaller and smaller. Isn't that true? Question is this, ladies and gentlemen. Now that we see this infinite geometric series, here's the question I'm going to pose to ourselves. Does this series have a sum? Does this series have a sum? Does it have a sum? If you add all these fractions up, remember there's an infinite number of them. It goes on forever. The fractions are getting smaller and 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 smaller. But you're adding an infinite number of them together. Do you think that this infinite geometric series has a sum? Does a sum exist? I want to draw your attention to a very interesting picture in your textbook. Let's go to our textbook. Now my program timed me out. I got to log back in, so do bear with me. I got to go get the textbook, the ebook. So hold on. All right. Okay, let's go to page 716 in the textbook. Page 716. Wait a minute here. Ladies and gentlemen, check this out. If I take a circle, one whole circle, and I start to subdivide it up into smaller and smaller and smaller little pieces. Here's a piece of size 1/2. I have 1/2 and I get 1/4. 1/2 of 1/4 is 1/8. 1/2 of 1/8 is 1/16. 1/2 of 1/16 is a slice that's even smaller, 1/32. 1/2 of 1/32 would be a slice that's even smaller, 1/64. Half of 1/64 would be a slice that's even smaller, 1/128, etc., etc., etc. Ladies and gentlemen, I know the slices of this circle are getting smaller and smaller and smaller as these fractions are getting smaller and smaller and smaller. But what do you think that those infinite number of fractions must add up to? What would be your guess? What would they have to sum up to?
Infinite.
No, it's not an infinite sum. What is it?
100.
No, not 100. Just how about what? If you take all these fractions, 1. Who said that? Okay. Ladies and gentlemen, do you agree that if you add up these infinitely smaller and smaller and smaller and smaller slices of this circle, infinite number now, you agree eventually they're going to fill out the entire circle? Do you agree? Eventually they will literally fill out the entire circle. So it seems to me that the sum of all these infinite number of fractions that are getting smaller and smaller and smaller would be equal to one whole circle. Isn't that bizarre? One whole circle. Seems to me like this geometric series, despite it being infinite, the sum would exist and it would have to be 1 equal to 1. I don't know if that circle argument helped you to realize that, but that would be the case. Okay. So yes, it looks like, yes, it does look like the sum exists. In fact, ladies and gentlemen, let's take a look at something here. The common ratio is what? For this geometric sequence here, the common ratio is 1/2, because to move from any term to the next term, you got to keep multiplying by 1/2. Isn't that true? All right. Notice these fractions, which are generated by taking 1/2 by the times the previous fraction. In general, if we analyze 1/2 to the nth power here, now what happens as I let n grow without bound? If I let n approach positive infinity, as I let n approach infinity, what's going to happen to the size of these fractions? They're going to approach what value? Can't we clearly see that 1/2 is greater than 1/4, which is greater than 1/8, which is greater than 1/16, which is greater than 1/32, which is greater than 1/64, et cetera, right? In other words, we can say that 1/64 is less than 1/32, which is less than 1/16, less than 1/8, less than 1/4, less than 1/2. What are these fractions really approaching here? What would be your guess? What number are they really approaching? As n gets larger and larger and larger, what are these fractions really approaching?
0.
0. You know, it looks like these fractions are approaching, or we say converging to 0, or converging to 0. So in calculus, ladies and gentlemen, the first thing you run into in calculus 1 is something called the limiting concept. So we would say the limit as n approaches infinity of 1/2 raised to the nth power would be 0. The limit would be 0. This is like, think of it as like kind of approaching a speed limit. It's approaching the inevitable speed limit of 0, where it can never ever be anything different, okay, as n grows without bound. All right. So we can see that these fractions are approaching 0. So yes, you know, we continue to add fractions, an infinite number of fractions, but ladies and gentlemen, these fractions are getting closer and closer to 0, which means the further you go out to the right in this series, the fractions that you have are contributing less and 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 less to the what sum, overall sum. Do you agree? But they're still contributing, don't get me wrong. But they're contributing less and less because they're getting smaller and smaller. They're approaching 0. All right. Okay. So yeah, we would say this sum here is approaching 1. Or, ladies and gentlemen, we would say as n approaches infinity, since 1/2 to the nth power is approaching 0, we would say the sequence of partial sums n is approaching 1. Approaching 1. So this series, this infinite series, is approaching 1 as n approaches infinity. All right. Since this infinite geometric series is actually approaching a finite defined real number sum of 1, we would call this infinite geometric series, ladies and gentlemen, this infinite geometric series, we give it a name. It's called a convergent geometric series. We say it is converging. It's a convergent geometric infinite series. It's a convergent geometric infinite series, okay? Or a convergent infinite geometric series. Maybe I should have put the word infinite before the word geometric. But we say that this series is converging, and it's converging to a sum of 1. We say the terms of the sequence, the geometric sequence, are converging to a value of what? 0. The terms of the geometric sequence are converging to 0. So not only is this a convergent geometric series, this is a convergent infinite geometric sequence. This is an infinite convergent geometric sequence. Okay. Any questions about that there? So notice this infinite geometric sequence or series, excuse me, converges. How about this next infinite geometric series? Do you think it might be convergent? Let me show you this one now. 2 plus 4 plus 8 plus 16 plus 32 plus 64 plus 128 plus 256 plus 512 plus 1024 plus ... This, ladies and gentlemen, is called an infinite geometric series. This is an infinite geometric series here. Does the sum of this series exist? Do you think there's a sum to this geometric series, ladies and gentlemen? This infinite geometric series?
I don't think there is for this one.
Okay. The associated geometric sequence would be 2, 4, 8, 16, and on this goes. This is an infinite geometric sequence, the associated infinite geometric sequence to this infinite geometric series. Now, you indicated that you don't think the sum of this exists. Why not? What would be your line of reasoning?
There's no number that it'll approach that can't be multiplied by the R variable.
Okay. What's happening to the terms of this sequence? Are they getting smaller and smaller and smaller like the last problem, or are they getting larger and larger and larger?
They're getting larger and larger and larger.
Yeah, these terms of this geometric sequence are growing without bound, we say, ladies and gentlemen. There's no bound to, there's no ceiling for these terms. Do you agree? In other words, these terms are going to continue to get larger and larger and larger and larger and larger and larger. Respectively, we would say more accurately, as n approaches infinity, we would say that the terms of this geometric sequence also approach what? Infinity. Does that make sense? Ladies and gentlemen, we call this a divergent infinite geometric sequence, a divergent infinite geometric sequence. Because these terms are growing without bound. There's no ceiling. Now, the terms of the last sequence we looked at, that was a convergent infinite geometric sequence. It was convergent. It was convergent, ladies and gentlemen, because there's actually a what? There's actually a lower boundary for these terms. It's called 0. Do you agree? There's actually a lower boundary for these terms of this infinite geometric sequence. And the lower boundary is 0. You see, these terms of this sequence are approaching some finite defined real number value called 0. This is a convergent geometric series. But this one, these terms are not approaching any finite defined real number value. These terms are just blowing up uncontrollably, getting larger and larger and larger. This is said to be a divergent infinite geometric sequence. And therefore, we would suspect that, think about it, if you keep adding larger and larger and larger and larger numbers, is this series ever going to settle down towards any finite defined real number value? What do you think? Think it's ever going to do that?
No.
Never. It's just going to keep getting larger and larger and larger. This series, this sum is going to keep growing infinitely large. And so as n approaches infinity, not only are the terms of the associated geometric sequence getting larger, approaching infinity, but ladies and gentlemen, the sequence of partial sums would also be approaching positive infinity. So for that reason, this is called a divergent infinite geometric series. Divergent. There is no sum, in other words. Divergent infinite geometric series. So the answer is the sum does not exist. Does not exist. Okay, so not all infinite geometric series, ladies and gentlemen, have a sum. Not all of them do. Some do, but in order to have a sum, the infinite geometric series has to be a convergent geometric series. So only convergent geometric infinite series have a sum. Have a sum. Divergent infinite divergent series do not have a sum. Don't have a sum. Okay. So in order to possess a sum, an infinite geometric series, and in general, an infinite any type of series must be convergent. Any infinite series, ladies and gentlemen, that is divergent will not have a sum. Not going to have a sum. All right. Now, there's another very important fact. If for an infinite geometric series, if, ladies and gentlemen, the common ratio R is greater than 1, or the common ratio is less than -1. Greater than or equal to 1, or less than or equal to 1, then the series diverges and hence would not have a sum. If, on the other hand, your common ratio of your geometric sequence is a fraction between 1 and -1, then it's true that R raised to increasingly larger and larger powers will always approach 0 as n approaches infinity. That will always be true. And the series will be convergent. Will be a convergent geometric series if the common ratio is a fraction between 1 and -1. If the common ratio is greater than or equal to 1 or less than or equal to -1, you'll have a divergent geometric series. You will not have a sum for the infinite series. If, however, your geometric series is convergent and R lies between -1 and 1, then it's always a fact, well-known fact, that as n approaches infinity, the terms of the associated geometric sequence will always approach 0. As evident with that one with the fractions getting smaller and smaller and smaller and smaller and smaller and smaller and smaller. Okay. If that's the case, ladies and gentlemen, if we do have a convergent geometric series where R, the common ratio, lies between 1 and -1, then the partial sum formula, which looks like this, as we allow n to approach infinity, ladies and gentlemen, we know that R to the nth power approaches what? 0, which would imply that your nth partial sum would be your first term times 1 minus R to the nth. But what's R to the nth? R to the nth is approaching what? 0, right? So this basically, this term drops out to 0 because as n gets large, this term gets smaller and smaller and smaller and actually eventually, approaches 0. Gets closer and closer to 0. So we can just say this is 0. And this nth partial sum formula then becomes what's called the sum of an infinite number of terms of a convergent geometric series. So now the sum of an infinite number of terms of a convergent geometric sequence is this new formula, which is just to say it's your first term of your geometric sequence divided by 1 minus the common ratio. This, ladies and gentlemen, is a very important formula that enables you to find the sum. This enables you to find the sum of an infinite. What kind of geometric series or sequence must it be? Convergent or divergent?
Convergent.
So this will enable you to find the sum of an infinite convergent geometric sequence. And in order for our geometric sequence to be convergent, ladies and gentlemen, what must be true about the common ratio? Do you remember? R has to be between what and what?
-1 and 1.
Between +1 and -1. Meaning R could be like a fraction, like 1/2, or R could be like -2/3, or r could be equal to 3/4, or any sort of fraction between 1 and -1. As long as your common ratio is some fraction between 1 and -1, the infinite geometric sequence is convergent, which means the infinite geometric series will indeed have a sum. And that sum is going to be generated by this formula right here. Everybody see that there? So that's an important formula to know. If, on the other hand, ladies and gentlemen, the absolute value of r is greater than or equal to 1, that's enough to say with this. And by the way, this is implying then that r would be less than or equal to -1, or r is greater than or equal to 1. Then what would be true? The infinite geometric sequence is what? Convergent or divergent?
Divergent.
Be divergent. And the infinite geometric series has no sum. It doesn't exist. Okay, there's no sum, does not exist. If, on the other hand, the absolute value of r is less than 1, what's this implying? The absolute value of r being less than 1 is implying that r is either what? R is less than between 1 and what? -1? That's what this is implying. Say the absolute value of r is less than 1 is implying that r has to be greater than 1, -1, and at the same time, less than 1. If this is true, then the infinite geometric sequence is what? Convergent. So the infinite geometric series has a sum. The sum would exist. Okay. All right, just a couple more problems. We can wrap it up. Any questions about this? What it means for a geometric sequence to be convergent or divergent, and the implications it has for the infinite geometric sum or series, possessing or not possessing a sum. Let's just try a couple of remaining problems here for section 8.3. Let's try to find the sum of the infinite geometric series 1 + 1/6 + 1/36 + 1/216 plus ... on and on that goes. I have a question for you, ladies and gentlemen. The associated geometric sequence is 1/1/6, 1/36, 1/216, ... What would be the first term of the geometric sequence? What's the common ratio? What's 1/6 divided by 1? That should be the same thing as 1/36 divided by 1/6. Well, whatever. It's equal to 1/6. Common ratio is 1/6. I have a question for you, ladies and gentlemen. Is my common ratio between 1 and -1?
Yes.
But notice 1/6, which is my common ratio, lies between 1 and -1. So this infinite series, is it convergent or divergent? Convergent or divergent?
Convergent.
Convergent, which means the infinite sum must exist. So to find the infinite sum, ladies and gentlemen, we use our infinite sum formula here. That's all we got to do. Use our infinite sum formula. So what's my first term? 1 over 1 minus what's the common ratio? 1/6? You know, it's amazing. Kind of boggles the mind when you really contemplate and think about this. Here you're adding an infinite number of terms together. Infinite, which means there's no end to the number of terms you're adding together. It goes on forever. And yet that sum converges to this one finite little real number. Isn't that amazing? That's pretty amazing when you really think about that. How can infinity become finite, equal to a finite number? Bizarre, but it is. All right, anyways, we got 1 over, another name for 1 is 6/6. 6/6 minus 1/6 is 5/6. So therefore the infinite sum must be 1 divided by 5/6, which is to say the infinite sum must be 6/5. Ladies and gentlemen, these infinite terms add together to give you a sum of 6/5. That is the sum of this infinite geometric series, 6/5. Or 1 1/5. Or 1.2. There's your answer. Isn't that neat? So when you add up an infinite number of these terms of this convergent geometric sequence, the sum is 1.2 or 1 1/5 or 6/5. Any questions how we computed that infinite geometric series? Okay. How about this one? Find the sum of 2 plus 8 plus 32 plus 128 plus ... Ladies and gentlemen, what's my first term? First term is 2. What's the common ratio? It'd be 8 divided by 2, or it would be 32 divided by 8, or it would be 128 divided by 32. In either case, you would get 4 for the common ratio. My common ratio is 4, but do you agree that 4 is greater than or equal to 1? Therefore, we would say this is what kind of infinite geometric series? Convergent or divergent?
Divergent.
Divergent. This is a divergent infinite geometric series. And therefore, ladies and gentlemen, the sum does not exist. There is no sum. This sum just keeps blowing up. Do you agree? Growing without bound forever. There is no sum. How about this one? They give us summation notation. The index of summation ranges from 1 to infinity. So this is an infinite sum. 2/3 raised to the j minus 1 power. Let's write out the first several terms so we can get a better feel for this series. Let j start at 1. So we'd have 2/3 raised to the 1 minus 1 power, or it would be 2/3. Well, I'll just write that down. Then j goes to 2. So then we have 2/3 raised to the 2 minus 1 power. Plus 2/3, then j increments to 2. 2/3 to 2 minus 1 power. We already have that. I'm sorry. Then j goes to 3. Be 2/3 to 3 minus 1 power. Plus on and on this goes forever. So this is really going to be 2/3 to the 0 power, plus 2/3 to the first power, plus 2/3 squared. I'll bet dollars to donuts. The next one will be 2/3 cubed, plus ... On and on that goes. Ladies and gentlemen, I got a question for you. What's 2/3 to the 0 power? Caleb, try to redeem yourself. What's 2/3 to the 0 power?
1.
1. Anything to the 0th power is 1 except 0. 0 raised to the 0th power is called an indeterminate form. But anything else to the 0th power is 1. So, ladies and gentlemen, what do we know? We know that our first term is 1. What's my common ratio? 2/3 divided by 1, which is 2/3. Is my common ratio a fraction between 1 and -1? The answer is yes. So this is a what? Convergent infinite geometric series. Therefore, we should be able to find the sum of an infinite number of terms of this series by using our formula, our infinite sum formula. first term of this series or sequence is 1. The common ratio is 2/3. Therefore, the infinite sum would be 1 divided by 1 minus 2/3 is going to be 1/3. 1 divided by 1/3 is 3. Ladies and gentlemen, that would be the sum of this infinite geometric convergent series. It would be 3. So if you add up an infinite number of terms of this thing, the sum would have to be 3. Okay? We understand what happened there. So the sum does exist because that's a convergent infinite geometric series. All right. One last problem, ladies and gentlemen. What time is it right now? We're right up. We're doing all right. We're doing all right. We're holding our own. I shouldn't be saying that. That were the last words of the captain of the Edmund Fitzgerald. We're holding our own. We're doing okay. All right. Let me just say that until the internet disappears on us again. All right, ladies and gentlemen, does that make sense? We got a sum of 3 here. That problem there? Any questions? This group never has any questions. That's awesome. A, either all of you are getting this perfectly and you're all cruising along, or B, I'm not sure what to think for option B. Okay. All right. So, ladies and gentlemen, let's try this. One last problem. Repeating decimals are interesting. If I got 0.8 with a bar above this, what does this mean here? That 0.8 with the bar above it. What does that notation mean? Anybody? What does that notation mean? You ever seen that notation before?
Yeah,
What does that mean?
it's been a long time. I don't remember.
Oh, it means we have a repeating decimal. What digit do you think repeats forever here?
8.
8.
8 does, yeah. That's a very compact way of saying that we have a repeating decimal where the 8 repeats forever, literally to infinity. If I had this decimal point, let's see, 128, what digits would repeat now for this one?
The 2 and the 8.
Just a 28. So this would be 0.128, 28, 28, 28, 28, etc. Correct? If I had this one here, 0.512 with the bar above all these, what digits repeat now?
The 5132.
512, 512, 512, 512 forever. Do you agree? All right, let's go back to this one here. Liz, I'm going to show you how to write this as a fraction. Okay, I'm going to show you how your frac function on your calculator really works and converts this into its equivalent fractional form. Check this out. Do you agree this repeating decimal, where 8 repeats forever, could be written as 0.8 plus 0.08 plus 0.008 plus 0.0008. Is this making any sense, ladies and gentlemen, that would be the
Yes.
case? You see
Yes.
that there? Interesting, huh? Now, do you agree that we would write this as what fraction here? 0.8. How do we write this as a fraction? How do we read it? It's 8 what?
8/10.
8/10. We write that as 8 over 10. And do you agree we read this one as 8 what? 8 hundredths. Next one is 8 thousandths. The next one after that would be 8 10,000ths. See what's going on here? Etc., etc., etc. But ladies and gentlemen, do we have maybe a geometric series here? Infinite geometric series? What would be my first term? Just 8/10.
8/10.
Now, what's my common ratio? Well, what do you got to do this fraction? What do you got to multiply this fraction 8/10 by to get to the next one? What do you have to multiply 8/100ths by that same number to get to the next one, to the next one, to the next one? Well,
1/10.
you can take 800ths here and divide it literally by what? 8/10. And what's 800ths divided by 8/10? I think you'll discover this gives you what? 1/10. Do you agree? The common ratio is 1/10. Makes sense. 8/10 times 1/10 is 8 over 100. 8 over 100 times 1/10 is 8 over 1,000. 8 over 1,000 times 1/10 is 8 over 10,000, etc., etc. But look at my common ratio is a fraction that lies between 1 and -1. So is this infinite geometric series convergent or divergent?
Convergent.
It's convergent, which means the sum exists, which means, ladies and gentlemen, I should be able to rewrite this repeating decimal as this infinite sum, which is to say it's my first term divided by 1 minus r. My first term is what? 8/10 divided by 1 minus the common ratio, which is 1/10. Let's try to work this out now. So we have 8/10. What's 1 minus 1/10? 1 is another name for 10/10. What's 10/10 minus 1/10? Gives me 9/10. 8/10 divided by 9/10, ladies and gentlemen, gives me what? What's 8/10 divided by 9/10? Isn't that 8/9? Well, I'll be darned. Look at that. Get on your calculator, ladies and gentlemen. Take 8 divided by 9. Do you get that repeating decimal? 8 divided by 9. You get the
Yes.
0.888888. You see that? Isn't that cool? So you're wondering how your frac function on your calculator would convert this repeating decimal into the fraction of 8/9. That's how it does this. It's using an infinite geometric series here, ladies and gentlemen. Pretty neat how that works, huh? Just wanted to show you one like that. It's pretty cute. All right. Well, ladies and gentlemen, I've worn out my welcome today. And I'm sure a lot of you are thinking I've worn out my welcome for the entire semester period. Do you agree? Yes, there's an end to this course, ladies and gentlemen. It ends on Monday. I'm going to go over one last section, 8.5. Now, when I make available the chapter 6 quiz on Alex and the chapter 7 and 8 exam on Alex, section 8.5, ladies and gentlemen, unfortunately will not be on the quiz or the chapter 8 quiz or the chapter 7 and 8 exam, because I will not cover that till Monday. However, you might find a couple of questions on your final exam from 8.5, the binomial theorem. Okay. Does that make sense?
Okay.
All right. So I will let you go. I hope you have a great, safe weekend, ladies and gentlemen. Try to get that Christmas shopping done and have patience on the roads. Just be careful. There's a lot of traffic. Just, drive safely. Unless there's any questions, I will let you go. Have a good one. Hopefully I'll see you on Monday to close it out.